When I've explained these circuits, we have already a complete receiver. What you see is the dBm, the filter, and at the left the preamp. This is the schematic for the filter and how I connected the preamp. For the dBm you need 7 dBm signal, and since the clock is about, of the 5351 is about 9 milliwatt, that's what I measured, and it has an impedance of 85 ohms. I added 33 ohms resistor, so then you come here to 50 ohm, and because we need about 5 milliwatts, we need half of what we have, so a 3 dB attenuator is added with these values, and when you connect those together you come here to the standard values of 39 ohm, and here I took 10 ohm and here I took 150 ohm, and I had about 5.4 milliwatt into the dBm. Let's go into the filter. For the schematic of the band filter I used ELSI. This is the schematic. It says what the resonance frequency is of the individual RC components, and we have a small coupling here and here a small coupling, and we have in and output capacitors. These small capacitors I made just by twisting some hard wires with insulation, of course, and that made the capacitor. And these are trimmers with also, because the trimmer has too less capacitance, I added some fixed capacitors to that. For the diode current, for the switching diodes, I don't use a fixed capacitor here, but I make just some turns here, I show later. If I choose plot, it shows what the shape will be of what will pass and what will be rejected. For example, here it says it is about -8 dB in the pass band, and rejected is about 50, and here about 60 dB. And I measured it with the NWT 6000, and with this overlay I show that it is really complying with the prediction. With the mini ring core calculator, I will put a link below, you can see that I made some calculations with it. I had some cores with the color yellow, and that seems to be the T37-6, they were small. You can see what the dimensions are, and suppose that I need the inductance of 333 nanohenry, then you need 11 turns, and the length of the wire is also given. That's very handy, otherwise you don't know what length to start with. And you can change here the strange values that are generated by ELSI, and the number of turns shows up. And because I use trimmers, it isn't too critical in this case. And I didn't make it coupling with the capacitor, but with a few windings over the last coil, and depending on the diode current via the RX or via the TX, you come to the signal this direction or this direction coming from. And the amp is with a BF982, a dual gate MOSFET, and it's connected to a relay, and that relay is operated in a way that it is switched to ground during transmit, and to the low pass filter at the end, the final low pass filter. So it is always connected to the amplifier. So I didn't switch the transmitting signal, I only switched the receive signal to ground. The schematic of the preamp: LC defining the frequency of operation, and because I had some oscillations, I added a 1K resistor to the coupling winding here, and the second gate, the gate 2, was first operated at half the voltage, so it doesn't really matter what values you take here, but to bring back the gain, I changed some values to lower this G2 voltage. The end is normally or often also with a coil that is on the resonance frequency, but in this case I took a broadband transformer to prevent oscillations, and of course RX voltage on it. My NWT6000 delivers about 1 milliwatt. So when I swapped this preamp, I added a 50 dB attenuator at the input, showing about 40 dB of gain, because we have minus 10 here, plus 50 is about 40 dB of gain. The red line, however, is when I added the attenuator at the output of the preamp. So it means we do about 1 milliwatt input, and it is amplified about 17 dB, so roughly to 50 milliwatt. That is here the output. Okay, that's it for now, and the next time we will see the further transmission chain amplifier.